For the past 100 years, starting around 1916, scientists have anticipated a remarkable development in the study of black holes, which are among the most enigmatic and captivating phenomena in the universe. These cosmic giants possess immense power, yet they remain almost undetectable. Some black holes are thought to be 2 to 4 million times the mass of our Sun. Thanks to decades of research, we have moved from knowing virtually nothing about these objects to uncovering more details up close. Recently, physicist Michio Kaku announced that we may finally have a view of what lies within a black hole. This groundbreaking insight could illuminate aspects of science that we may have overlooked. The basics of black holes. Before delving into the specifics of Kaku's findings, it's important to understand black holes. Though many have a basic idea, gaps in knowledge persist. In 1916, Albert Einstein published his theory of general relativity, which predicted black holes. At the time, they were purely theoretical. It wasn't until the 1960s that scientists found evidence of their existence by studying the constellation Cygnus, where they observed a bright blue star emitting X-rays while orbiting a massive, dark object. This observation led to the term black hole, and confirmed that these were not simply products of Einstein's imagination but real entities in space. One of the first studied black holes, named Cygnus X1, is located about 6,000 light-years from Earth. This object was brighter than the Sun by orders of magnitude, and had a gravitational pull so strong that even light could not escape it. Black holes, therefore, are not just regions of space. They are areas where gravity is so intense that nothing, not even light, can escape. As a result, anything that comes too close is drawn in, never to reappear. Gravity and the nature of black holes. The defining feature of black holes is their gravitational force. They act as cosmic vacuum cleaners, compressing anything that enters until it reaches a singularity, where physical laws break down. If a person were to fall into a black hole, they would be stretched into a line, a process known as spaghettification, before ultimately perishing in the intense gravity. Despite these dangers, the scientific importance of black holes makes them crucial subjects of study. Today, scientists believe there could be over 100 million black holes in the Milky Way alone, each with unique properties and behaviors. In 2021, scientists captured the first clear image of a black hole, specifically the one at the center of the galaxy M87. This image revealed that black holes are not just single voids. They have layers. The first layer, known as the event horizon, is the point of no return. Beyond it, everything is pulled in. The next layer, the photon sphere, is where light orbits the black hole. Lastly, there is the singularity, where everything is compressed into an infinitely small point, defying conventional laws of physics. Challenges in studying black holes. One of the greatest challenges in studying black holes is their inaccessibility. Researchers can't directly observe them. Instead, they rely on the radiation emitted from surrounding gas and dust. Any spacecraft that attempts to enter a black hole would be crushed upon reaching the singularity, rendering in-depth exploration virtually impossible. Therefore, scientists study black holes indirectly, piecing together information from surrounding phenomena, such as the movement of stars and gases near them. Each black hole operates under unique conditions, which makes studying them even more challenging. Many theories suggest that black holes form from collapsing stars. When a star exhausts its fuel, it can no longer generate enough energy to counteract gravity, causing it to collapse into a singularity. To investigate the core of these phenomena, NASA scientists have observed the center of the galaxy M87, where they noted a swirling vortex of hot hydrogen gas moving at over 1 million miles per hour. This mass, believed to be equivalent to 2 to 3 billion suns, prevented the gas from dispersing, indicating a black hole's presence. Theoretical advances and the future of black hole research. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe rotating black holes, laying the groundwork for future theoretical exploration. As scientists continue to study these objects, they hope to uncover even more about their nature and potential impact on our understanding of the universe. The phenomenon of black holes suggests that instead of collapsing into a singular point, they might form a structure resembling a ring of fire or a fragile disk. This region surrounding a black hole is termed the ergosphere, where the laws of physics begin to diverge. Theoretical physicists have also speculated about the existence of an Einstein-Rosen bridge or wormhole, which is a hypothetical passage through spacetime that connects two distinct areas of the universe, or even two parallel universes. If one were to fall into a black hole, rather than being crushed, they might be pulled through a fiery tunnel and emerge from a white hole in an alternate universe. To understand how this concept operates, it helps to visualize spacetime as a four-dimensional fabric that Einstein theorized. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Picture a piece of paper as a representation of spacetime. If you place 2 points on it and draw a line between them, it illustrates how objects traverse through spacetime. Now, if you could fold the paper to create a shortcut between those 2 points, this would represent a wormhole, essentially a shortcut through spacetime that connects two distant locations instantly. Wormholes are not merely a figment of science fiction. They arise as a consequence of general relativity. However, no one has directly observed one yet. The stability of wormholes is a point of contention, as they may collapse almost instantaneously. The existence of an Einstein-Rosen bridge would imply that black holes are not just massive vacuum cleaners but could also serve as gateways to other regions of spacetime. The potential use of wormholes for travel through space and time is fascinating, yet remains speculative. Even if we could stabilize a wormhole, it is unlikely that we could use it for faster-than-light travel. According to Einstein's theory of special relativity, the speed of light serves as an ultimate limit on how fast anything can travel through spacetime. Nonetheless, the theories surrounding wormholes and black holes as conduits to different parts of the universe or different times have captivated physicists for decades. One of the most intriguing concepts in this area is the Kerr wormhole, named after Roy Kerr. This theoretical wormhole could connect two distant points, potentially allowing travel to alternate universes or different times within the same universe. The Morris-Thorne wormhole is another example, shaped like a ring, reminiscent of the mirror in Alice in Wonderland. Passing through it could hypothetically transport someone to another universe or time with different physical laws. While the concept of wormholes as means of interstellar or time travel is thrilling, it also poses significant challenges. Some physicists argue that wormholes, particularly Morris-Thorne wormholes, may be inherently unstable or difficult to navigate due to extreme radiation and subatomic forces. Critics point out that the equations used to describe wormholes and black holes primarily address gravity, failing to account for the quantum forces that govern radiation and subatomic particles. To truly understand these phenomena, a new theory that integrates gravity with quantum mechanics is necessary. Physicist Michio Kaku has been working on a theory of everything for many years, with string theory being the most promising candidate. This theory posits that subatomic particles are tiny, vibrating strings and that the universe is composed of these strings, similar to how different musical notes correspond to various vibrations of a violin string. String theory also explains many puzzling phenomena by showing that as strings move through time, they warp the fabric of spacetime, potentially giving rise to black holes, wormholes, and other intriguing solutions to Einstein's equations. However, the extra dimensions of spacetime suggested by string theory are so small that we cannot directly observe them. The most precise measurements in our laboratories currently only utilize the 4 familiar dimensions: length, width, depth, and time. One possibility is that these extra dimensions are tightly curled up, making them invisible to us, like a piece of paper tightly rolled into a cylinder. If you were an ant walking on that paper, you wouldn't perceive the curvature. Likewise, the additional dimensions in string theory may be curled up into tiny loops or twists that are imperceptible, yet they influence the behavior of the strings vibrating within them. Another theory posits that these extra dimensions might have been more prominent at the universe's beginning, during the Big Bang. In some variations of string theory, the universe began in a state of 10-dimensional spacetime, with all dimensions equally visible. As the universe expanded and cooled, the extra dimensions collapsed and curled up, leaving us with the 4 dimensions we recognize today. If this hypothesis is correct, we might find evidence of these additional dimensions in our surroundings. The mathematics involved in string theory is incredibly complex and has opened up new realms of scientific inquiry. However, addressing the problem of a quantum black hole has proven elusive. Despite many physicists' attempts, no one has yet succeeded. Edward Witten, from the Institute for Advanced Study in Princeton, has referred to string theory as 21st century physics that accidentally fell into the 20th century. Recently, some physicists have reported significant advancements, suggesting that string theory might completely resolve the issue of quantum black holes, albeit only in 2 dimensions, not 10. Many believe it is only a matter of time before someone successfully tackles this challenge. Until then, it is premature to anticipate intergalactic or time travel adventures. One thing is clear: there are simply too many questions and even more potential solutions. Michio Kaku's string theory introduces an intriguing twist. Perhaps the Big Bang was not as cataclysmic as commonly perceived. It wasn't necessarily a colossal explosion or a loud noise, as one might expect. Current theories of the universe's origins do not adequately explain what caused the so-called bang or how it unfolded. They only assert that it happened. We need a theory that elucidates what transpired before the Big Bang. String theory proposes that our universe might have formed from the collision of 2 separate universes or emerged from another universe, akin to a child being born from its mother. This connection between universes is reminiscent of a wormhole, much like a tunnel linking 2 bubbles. We might have already discovered evidence of this umbilical cord connecting our universe to another, suggesting that we could be living inside a black hole, oblivious to it. Since we exist in 4 dimensions, we are unable to perceive what lies beyond them. It's entirely possible that we reside within a black hole, while the black holes we observe are actually wormholes leading to different dimensions.